Hey guys, welcome to the second lesson in the topic of solutions. We're going to be talking about molarity. Before we get started, I just want to tell you a little story. Times New Roman walks into a bar and the bartender looks at him and says, "Sorry, we don't serve your type here." Do you get it? Get it? All right, let's get rolling here. I know it's a bad joke, but what are you going to do? So what is molarity? Molarity is the moles of a solute per liter of solution. So molarity is moles of solute per liter of solution. And I just want to clarify some things because students will see this molarity written different ways and they often get confused. Molarity is represented with a capital M. So a capital M is the symbol for molarity. So if you see 1.5 capital M, that means that it's a 1.5 molar solution, or the molarity is 1.5. This molar and molarity confuse students because we're learning about moles and then they say like, well, what's molar? Molar is molarity. So these all mean the same thing. And it's represented with a capital M, which means moles per liter. And this is moles per liter is a lot like what we did with molar mass, grams per mole. And you can use dimensional analysis to convert in and out of things because you have this relationship of a mole per liter. This is useful to convert from moles of something or inversely and directly into volume of something. If you know the molarity, you can convert moles to volume. I think it's easier when you're dealing with solutions and things are measured in molarity because you don't need the periodic table like we do with grams to moles. All you have to do is know the molarity and you convert from moles to liters. We'll see. We'll practice with that, this topic. So just a little example of how this is applied. What is the molarity of a 2.0 liter solution with 3 moles of hydrogen chloride in it? Well, we're going to solve for molarity, where we're going to figure out the molarity, which is represented with a capital M, of a 2.0 liter solution. That 2.0 liter solution would be our denominator with 3.0 moles of hydrogen chloride in it, and that would be that 3.5 or 3.0 moles would be my numerator. And if I set this up like this, it's 3 moles divided by 2 liters, which would be 1.5 moles per liter. And a mole per liter is molarity. You can write it either way. You can write 1.5 moles per liter, or you can write 1.5 capital M. When we have solutions and things in lab, you'll start to, or you may have already noticed, that we'll have a number with a big capital M next to it. That's telling us the concentration. And the bigger the number, the more moles that are in it. So the bigger that number, the more concentrated it is. The smaller the number, the more dilute it is. So with that idea, let's talk about some problems here. Let's solve some things. What I'd like you to do is see with your prior knowledge and what I just talked to you guys about with molarity, can you apply it into these situations correctly? So if you would please pause the video right here, try to solve these 6 problems, and then start the video again, and I'm going to work them out and we can check if we agree on the answers or not. So paused, and now we're back. The magic of YouTube. All right, so let's try number 1. So number 1, we have, we've got 2 moles, 2.0 moles of sodium chloride, and it's in a 3.0 liter solution. So all we got to do is take 2 divided by 3, and with 2 significant figures in that question, I would record it as 0.67 moles per liter, or capital M, of sodium chloride. So it's a 0.67 molar solution of sodium chloride. Number two is very much like number one. What's the molarity of a solution that has 1.23 moles of potassium chloride in a 3.2 liter solution? So that's 1.23 divided by 3.2 equals 0.3, and there's two significant figures in this question. One of the numbers has three significant figures, but the other one only has two. So we have to answer it with two. So it would be 3.8 molar solution of potassium chloride. All right. Number three, how many liters? So this is a little bit different. I've got the molarity and I've got the moles. I want to solve for liters. And I'm going to set this up using dimensional analysis. You might have solved it a different way just by doing the formula and plugging in and rearranging. But I'm going to solve these using dimensional analysis because it will help, because we can and we will apply molarity into stoichiometry. And that was topic 9, and there's lots of steps in there. So I'm going to show you doing this with dimensional analysis. So I have 1.5 liters, and I know that the molarity is 2.1, which means 2.1 moles per liter. That's what molarity means. So liters cancel with liters, so this would be 1.5 times 2.1. And there's two significant figures here, so I would record this as 3.2 moles of lithium fluoride. 3.2 moles of lithium fluoride. Okay, let's look at number 4. Number 4, how many liters? So we're going to solve for liters when I've got the molarity and I've got the moles. I'm going to use the molarity as my in-between step to convert from moles to liters, because I know that that's 0.48 moles per liter. So let's do that. So number 4, I'm going to say I have 0.032 moles of potassium bromide, and I know that the molarity is 0.48 moles per liter. See, I inverted it this time because I had moles and I want to get rid of moles. So I inverted my molarity, just like we do with molar mass or what we do in stoichiometry. And so to answer this question, I would say 0.032 divided by 0.48. So this would be 0. And we have two significant figures in this answer, so 0.067 liters. I would need 0.67 liters to get 0.32 moles of the potassium bromide. Number 5, I've got liters and I got molarity, and I want to know how many grams of hydrogen chloride. So we're going to go back and we're going to have to use some molar mass situation here with the periodic table, because this is grams, not moles. We can do that though. So let's give it a shot. So number 5, I have 3.2 liters, and we know that there are 2.1 moles of hydrogen chloride for every 1 liter of this. So my liters cancel. And now I'm in moles of hydrogen chloride, but I'm going to go one step further, and let's convert hydrogen chloride into moles into mass. So hydrogen over here is 1.008 plus chlorine, which is 35. It's blurry, very blurry. Is it better over here? I don't know. It's 35, at least on my periodic table, 35.453. So the molar mass of hydrogen chloride is, oh, excuse me. I'll edit that out. All right, if I remember. For every 1 mole of hydrogen chloride, it is 36.461 grams of hydrogen chloride. Moles of hydrogen chloride cancel with moles of hydrogen chloride. And so let's do this. We're going to say that that is 3.2 times 2.1 times 36.461 equals. So I've got 245, but this question only has 2 significant figures. So remember, trailing zeros don't count if there's no decimal place. So let's not put a decimal place, and we'll write 2. That 5 is going to round the 4 up. So we'll put 2.50 grams of hydrogen chloride. All right. Hopefully that's what you got too. And let's look at number 6 together. Number 6, we've got molarity. So we've got our solution, a molar solution. I've got a mass, so I need to turn that mass into moles so I can use the molarity. And I've got milliliters. Now this is very common in lab. I'm not going to be giving you liters of solution. I'll be giving you milliliters. So knowing the conversion from liters to milliliters is very important. And hopefully you guys remember that there are 1,000 milliliters per 1 liter. So let's set this one up. I'll show you how I set it up. And like I said before, I set this up using dimensional analysis is the way I like to do this one. So actually, let's just get another piece of paper here. All right, so number 6. Boop, boop, boop. So we're going to say we're starting off with, I know you might think, how do I start? Well, I don't know where to start. I know molarity is I think of it as a conversion because it's moles per liter. I'm going to start off with my things that are just 1 unit. So molarity is moles per liter, 2 units. This is just 1, and that's where I start off with when I use my dimensional analysis. So I'm going to say that 0.97 grams of sodium hydroxide. Let's convert. I'm going to go grams to moles, moles to liters, and then liters to milliliters. That's my game plan here. So to add up the molar mass of sodium hydroxide, I'm going to use the periodic table, and I'm not going to bother focusing too much or showing you too much on those numbers because actually it seems to be clear right here. So anyways, sodium hydroxide is a sodium 22.990 plus oxygen 15.999 plus a hydrogen, which is 1.0008. So sodium hydroxide is the sum of those 3 elements, a sodium, oxygen, and hydrogen, and I come up with 39.997 grams of sodium hydroxide per 1 mole of sodium hydroxide. Now I'm going to use the molarity to convert, so grams are gone of sodium hydroxide. I'm in moles of sodium hydroxide. I'm going to use the molarity, which in the question it says I've got 2.5 moles of sodium hydroxide for every 1 liter of solution. Moles of sodium hydroxide. The moles of sodium hydroxide cancel with each other per liter of solution. And one last step I'm going to put in here is that for every 1 liter, there's 1,000 milliliters. So we'll do all that together. So that's my full setup. Grams of sodium hydroxide turn into moles of sodium hydroxide, turn into liters, turns into milliliters. That's the way I set it up. And let's see what the answer is. 0.97 times 30, oh sorry, that's clear. 97 divided by 39.997 divided by 2.5 times 1,000. With two significant figures, my answer is 9.7 milliliters. So the question is, if we go back to what the question is asking, it says, what volume would I need to obtain 0.97 grams of sodium hydroxide? What volume of this 2.5 solution would I need? And the answer would be I would need 9.7 milliliters of the solution to get 0.97 grams of sodium hydroxide. So I hope you understood how to work through these things, and save any questions for me next time you see me. I look forward to seeing you again. Take care.